MCell Blender to visualize the results of the model.
Awesome.
If that's how you want to do it. Okay, looks like people are mostly back. Okay, we may even have picked up a few people who weren't here earlier. Okay, so I think we're recording. Looks like there's some questions in the chat. Yeah, okay, and looks like everyone's happy in the chat. And I will start sharing my screen. And this is where we had left things. Let me move the gallery over to my other screen over there. Okay, and I'll make the chat window a little bigger, like that. Okay, so this is where we had left things. We have molecule A and B with our diffusion constants. We have molecule placements of release site 1, placing molecule A at 0, 0, 0, 1,200 of those. And molecule B at 0.2, 0, 0, 1,000 of those. And we're running for 1,000 iterations with a 1 microsecond time step. Okay, so that's where we had left things.
Please, if you hear me, can you maybe save the file and share it with the participants so everybody on the same side if they had some.
Okay. And I did prepare a location for milestones where I have put things. So let me save this as a milestone. This is maybe this is before the first milestone, so I'll call this milestone, maybe 0 or something. So I'll do a save copy in this directory, and I'll call it milestone 0, and I'll save that, and I'll move this over here, and let's see, CD cell modeling workshop 2021 organelle demo 1, and there's our milestone, and I'm going to SCP this file to a location that I'll show you where to get to it in a moment. This is going to go to Bartol at Quarter Public HTML/CMW 2181. Okay, there it goes. Okay, so where did that go? That went to, let me see, shrink this down. That went to this location right here on the guide. This is the link. You can just click on that link, but this is really http://cnl.talk.eu/Bartol CMW 2021. And in that location, if I click on it myself, takes you to this directory where there are resources for our tutorial and some other things. These are the milestones. So if you download this file called organelle demo milestone 0.blend and open that in Blender, you'll get exactly what I have. And later today, we're going to work with this model, organelle transport.bngl. This is the pure BioNetGen language version of the model that we're building here today. And this model is runnable in in BioNetGen, and you could load this into VS Code and run this model. I think it might be missing the actions section, but it's a compartmental BioNetGen model. Also, I'll show you later today that you could take this model. This was written by hand by Adam. You could take this model and load it into Cell Blender, and it will get imported and be turned into an MCell model in Cell Blender. And I'll show you how to do that later today. So you can go back and forth between BioNetGen language and MCell via Cell Blender or via VS Code, going back and forth in both directions with your model. And Adam will show more of what you can do with these models on Thursday. Okay, so I'm going to put this back over onto my other screen. So hopefully people have been able to, yeah, and I see Adam put that there. So that's the checkpoint file, and then that directory where that lives is where there'll be other milestones for our project today if anyone gets stuck. Okay. So to continue, so now we have a model with A and B. Let's add another molecule, and let's call it C. And again, it's a volume molecule, and let's give it diffusion constant 1e minus 6. Being very careful with that minus sign again. And you can see over here the colors that are automatically generated for each of the molecules. Let's just leave those alone for now, but I just wanted to point that out, that you could click on one of these color swatches and change the colors any way you like. And we'll be doing some of that a little bit later for good reason. Let's make it be a volume molecule, and you can see we get this little icon here next to the names, and this little kind of rubber ball bouncing kind of icon means it's a volume molecule. You'll see in a moment that we'll get a different icon for a surface molecule. And let's make a reaction. This will be our first reaction, because we now have two molecules that we can make react with each other. So go to the reactions tab and click on the plus sign to make a new reaction. And by default, when it pops up, you just see the arrow, because the reactants and products are both blank. And in the reactions, let's just write A plus B, just like that. And then the reaction type, you can see that we can have irreversible or reversible reactions with exactly the same syntax as in BioNetGen language, meaning it looks like a dash, greater than or less than dash greater than for the double-headed arrow. But we put it in a drop-down menu, so you can just pick which one you want. But let's leave it be an irreversible reaction. And then for the products, let's say we're going to make a product called C. And for the rate constant, for the reaction, let's make it be a really high rate constant, 1E9. And the units for the reaction, by default, the units for the reaction by default are per molar per second, as Jim explained yesterday. MCell will convert this into a probability of reaction per collision. As I explained in the lecture earlier today, we have that equation for relating the rate constant K and the diffusion constant and the time step and the size of the effector tile, relating that to a probability of binding per collision. And in this case, these are volume molecules, so there's not effector tiles, there's the interaction radius, which I'll explain where it comes from here in a minute. But by default, the interaction radius is about 5 microns or so. So it's about not microns, 5 nanometers, excuse me. The interaction radius by default is around 5 nanometers. I'll give the exact equation for it in a little bit. And so that means the diameter of the imaginary cylinder that's being swept out when the molecule diffuse is about a 10 nanometer diameter, which is about the size of many proteins in the cytoplasm. That's kind of a nominal amount. Okay, so and MCell uses this rate constant K in units of per molar per second, converts it into a probability of reaction per collision between the particles A and B. Okay, so let's make the rate constant 1E9. And for molecule placement, well, we don't have to place any molecules of C in the simulation because we have a reaction that's going to create molecules of C. Oh, and a moment ago I said let's make the diffusion constant be 1E minus 6. Let's change that for just a moment, just for fun. Let's let the diffusion constant for C be 0. Okay, this way, by making the diffusion constant 0, if you're hopefully you're following with me because I'm kind of maybe bouncing around a little bit. Let's make the diffusion constant of C be 0 so that when this reaction happens, the C particles will be left in place at the point where they were created by this reaction. Okay, and it's an irreversible reaction, so the molecules of C will be created and just stay there, frozen in space. Okay. And that's it. I'm going to save, and we're ready to run. But let's see, there's a question. Can we show the cylinder in Blender? Not with any of the built-in tools we've made, but everything is in Python here. So you could potentially make your own way of visualizing the molecules and their motions if you like, and actually draw the cylinders and actually maybe even draw a zigzaggy line made of cylinders that traces out the entire trajectory of the diffusing particles if you wanted to. That would be actually kind of fun to do, but we won't have time to work on that here. But it's a cool idea. Okay, so there's our model. We're ready to run it. So I'm going to clear the completed runs, go to the Run Simulation tab, clear completed MCell runs, and hit Export and Run. And it takes a moment to export, and then boom, there it is. It just ran, and now I'm going to say reload. And if I hit play, there it goes. And I'm going to close up the tab, and you can see there's the molecules of C being left in space at their locations where they're created. And I can look at it from different angles. Okay. So there's our reaction diffusion of A plus B goes to C in the case where I have A and B 0.2 microns apart with 2 different diffusion constants and that irreversible reaction. And I think you might be hard pressed to write down an analytic solution to solve the system that we just created. Although there might be a prayer of doing it since we're in open space and we're starting from point sources. There might be a prayer of being able to write down the an analytic solution to this, but I'm not sure. Oh, so Hydia asks, how could I stop, pause, run simulation to update the parameters? So in Cell Blender, we don't have a way to pause, but you can, but if the simulation were running, let me hit clear and run. what I'm going to do is I'm going to hit a run, and I'm going to say, oh, what if I accidentally made a mistake? I could select it here in the list and say kill. And then if it's killed, I'll get how far it had gotten along before I killed it, and I'll get an X here rather than a check mark to indicate that I've killed it. And then I can clear it and start it again. Oh, and start it again. So you can see that while it's running, I get the little running man icon while it's running. And when it completes, I get the check mark saying it's complete. Okay. Okay, so someone just asked a question about, can we make the C molecules look like the letter C? And the answer is yes, and that was the next thing. She must be reading my mind. That was the next thing I was going to show you. So back here in the molecules, we have A, B, and C as red, green, and blue little spheres. But why do they look like little spheres, and why are they this size? And what if that's not what I want? So under the display option, so if we go back to the molecules tab and say choose the molecule C, in the list of options below the molecule name and molecule parameters, you can see a tab called display options. If I choose display options, here again, I could change the color. I can change the size that it appears. And I can also change its shape. So here it says sphere 1, and there's a whole bunch of other shapes in here. But one of the fun shapes, for example, like this is a letter. And I could choose the letter C from this list. And so now the molecules of C look like little C's. And maybe I want them bigger than that. So I could maybe change the size to 2. And these are scale factors. And a factor of 1 means the default scale, which is about a diameter of about 10 nanometers. And so 2 would be 2 times that. So now these are about 20 nanometer little letter C's. And there they are. And if I single step through, you can see there they are moving. But I said we're not supposed to let these diffuse. And so they're not diffusing, but they are tumbling. And that's just a trick for visualization. In MCell, they're not really tumbling. In MCell, they're really point particles. And the tumbling here is just an option in the visualization system here. Okay, so there's our little letter C's. And we can do the same thing with the A and B. So let's do that. So for A, let's give it a shape letter A, and that's the default, so we don't have to change it. And there's the little letter A's. And let's leave them be the small size that they are. And then for the molecules of B, we can say letter, and let's change them to a letter B. And we'll just leave them B small. So there's the B's. And then I could run it, and there we go. Okay, A, B, C. So I'm going to hit save and save it again. Okay, so now we have our reaction between A, B, and C. So now let's change things up a little bit and go into the molecules tab for C, and let's give it a diffusion constant of 1e minus 6 and let them be diffusible. And save it, and then go to run and say export and run. So I see some people asking about the molecule structure tool. So we're not going to go over that during our workshop because it's a lot. We already have a lot of material to cover, but we'll prepare a tutorial about it on the MCell.org website, but it works with MCell version 3, and I don't think we quite have it working with MCell version 4 yet, but we will very soon. And what you can do with the molecule structure tool is define the orientation and bond lengths and dihedral angles of bonds between complexes when they form, especially useful when you use the BioNetGen language with the complex structured molecule form. And there is one of the tutorials is a formation of chains and coils showing examples of the kinds of things that you can have. And you can basically, with simple local rules for how the molecules assemble, create assemblies that form emergent structures of any conceivable shape that you can imagine. And right now, it's they're only visual representations that are seen in Cell Blender, but in the future, we're going to make it so that these structures actually are created in the MCell simulation and used during the collision detection. And so then, and with excluded volume, then we'd be able to have the assembly of all kinds of structures. And of course, polymerization is possible. And this example, simple chain, makes polymers, and the coil makes a coiled helical polymer. And all these things will be possible. And this is where we're heading pretty quickly, rapidly, moving forward from here, because we're very interested in what happens inside dendritic spines and actin cytoskeleton and the structure of the PSD and liquid-liquid phase separation. All these things are all related to these issues that happen with not just BioNetGen language structured molecules, but actually physically, spatially structured molecules. Okay, so we have this. And now this is all visualization. Now let's start quantifying what's happening in our reaction. So in our plot output settings tab, let's go there. We're going to add some observables. So the terminology here for reaction data output is kind of old terminology that we had used when we first invented MCell, before we met Jim and encountered their terminology for this, which is observables, which I think is a nicer term. We'll probably change this tab here so that it says observables, so that everything's compatible. And well, it is all compatible, but I mean, the terminology is all consistent. So again, to add a new observable, we click on the plus button to get one, and it comes up and it says name error because it wants us to name a molecule. And here it's going to give us a drop-down menu for naming some, for finding something in the list. So let's count molecules of A in the world. And world here is a keyword meaning the entire universe, not the object called world. We could count inside a named object, but we don't have any objects yet. We're going to have that soon in our model as we build it. But so this is going to count molecules in the world, molecules of A. And up here, when I choose that, it says count A in the world. And now let's add another one where we're going to count B in the world, and another one where we count C in the world. So now we're going to be keeping track of the disappearance of A and B as they react with each other, and the appearance or creation of molecules of C in the world over time. And whenever we add a new observable to the simulation, just like in BioNetGen language, we can't see it immediately. We have to, even though we just ran a simulation where all that was happening, we can't see it as an output until we run the simulation again. So here I'm going to go to the Run Simulation tab and hit Export and Run. And it's getting set, and there it goes. And it just ran. And of course, I hit reload. And of course, now the model runs exactly the same as it did before, except now we have the molecules of C diffusing and not staying in place where they, at the point where they're created. So they begin to diffuse immediately after they're created. So if we rewind this again in single step and look very closely, let me hide this. Sorry, I didn't mean to do that. Do this. I'm going to rewind, and we can look for the first moment in time when a C molecule is created. Look how cool this is. I can just like get inside here and look at this. Okay. Okay. At this moment, we have the first molecule of C being created, and then a second and third and fourth one way over here, and then from here, you know, we just get more and more and more of them being created, and of course, they're diffusing as they go. So if we look, for example, out here on the edge of the world, we can look at this one molecule of C, this one, we can just keep track of where it's going. Oh, and what's interesting about this is because the molecule shape C is shaped like a hoop, we can see this little vertex inside, and that's the actual physical location of the point particle that MCell is keeping track of. It's rendered here as a little point. Okay, that's pretty cool. Okay, so there we are. But we just asked for plot output. So we can go to the plot output settings tab again. And now that we've done a simulation, we can go down here and we can ask for a plot to be created. And there's options for the plotting over here, and the default plotter is the matplotlib plotter. But there's other plotters. If you have the software installed on your system, it will use XMGrace as a plotter. If you have Java installed, there's a Java plotter built in here. This is a matplotlib plotter, I think, but it's very, very simple and not as nice as this one. But we prefer the matplotlib plotter because it's a little bit richer in what you can do with it, but it's not as functional as the plotly plotter that you're seeing in VS Code. And there is a way to take the output that was just generated and view it in VS Code with the plotly plotter as if it were BioNetGen, as if you had generated in BioNetGen. But we might have time to show that at some point. Okay, so I'm going to say plot it. And by default, you get separate plots for A, B, and C, and the axes of the plots are scaled automatically by matplotlib. And you get a legend up here, and it's a little bit ugly. So let's choose a different option instead of saying one page, multiple plots. I'm going to say one page, one plot. And usually this works better if you have multiple quantities that you want to plot together on the same axis. And then I can say plot. And then I get my graph that looks like this. So you can see we start with 1200 of A, 1000 of B, 0 of C, and then this is the rate of formation of C. And you can see this has a very funny shape to it, and there's a little hook at the beginning because the particles are starting as diffusing point sources, and it takes it some time before they even reach each other, right? And we saw that. You know, if I go back to the beginning, you can see there it takes some time before even the first one forms, right? So you know that time is this little hook right here. And then they form rapidly at first, and then it slows down. And if you have a well-calibrated physics eye, you'll look at this and you'll say, that shape doesn't look quite like an exponential, right? It's too fast at first and then too slow later. This is like maybe multiple exponentials, you know, summed together or something. And so what's going on? And here, I bet you would be very hard pressed to write an analytic solution that gives you the shape of this curve. And of course, we're doing it numerically, so we're going to get the answer. You could do this with, PDEs or with this particle method that we're using here to get, to compute the shape of this curve. And what's going on is, at first, when the particles encounter each other, we have a very high concentration of A and B coming together. But then as time goes on, the A and B are moving away from each other. There's B molecules way over here that will never in their lifetime ever see an A particle. Some of these B particles will escape the system and diffuse away before they ever see a single A molecule. And so this reaction, theoretically, should go to about 1,000 molecules of C are possible because we have, there's an excess of A, but we have 1,000 molecules of B. And our reaction is A plus B goes to C. So B is limiting because it's in less amount. That's the limiting amount. But you can look here and you can probably project that this is never going to get to 1,000. Just looking at this, right? And I think that's correct, right? Because the molecules of A and B are in unbounded space, and they can diffuse off and get more and more dilute as they go, and they'll never see each other. Some of these molecules will never see each other. Okay. So that's this is the graph we get. Okay, there we go. So now you're maybe getting a hint about where I'm going next. Since there's no container containing these guys, they're never going to react with each other all the way. So let's make a container that is going to contain our A and B molecules. So I'm going to rewind time just so we can see what we've got here. And to add geometry to the model, we do that by going to the Model Objects panel. You could maybe change the name of this to be Model Geometry or something, but we call it Model Objects. And we have some tabs here that are shortcuts to some of the geometric primitives that are built into Blender for creating geometry. There are no restrictions for what kind of geometry you can create for your model, except that after you create it, you have to convert it into a triangle, a mesh made of triangles. And in Blender, any of the different ways of generating geometry in Blender, there's always an option to convert those into a triangle mesh surface mesh geometry. And so you're not limited to these primitives. You can do anything you want. In fact, this morning I showed you, the dendrites and axons and astrocytes that came from a 3D reconstruction, and those were all triangle meshes. So you can go wild with your mesh geometry if you want to. Okay. So what we're going to do is we're going to start by making an icosphere. We have cube, icosphere, a UV sphere, which is like a globe with longitude and latitude, cylinders, cones, torus, a planar sheet, a planar disk, and even a planar sheet, but divided up into a grid, if you want a grid for some reason. These are all good starting places for making lots of things. Let's create the icosphere. So I'm going to click on Add Icosphere. And you can click it, but I'll explain as you do that geometries are always created at the location of the 3D cursor, which is this little bug-shaped, hard to see it. It's because it stays constant size on the screen. This little bug-shaped glyph here, a circle with a cross through it. So geometries are always created at the location of the 3D cursor, I'll show you later how to control that. But let's click on the icosphere. And when it comes up with a default size and a default resolution. And we can control it by going down to this, this control panel that appears in the lower left corner that's closed up. So if I open up this, I have control over the icosphere. Oh, and I think I messed it up because I actually clicked on something before I allowed that to happen. So I'm going to delete the icosphere and start again. So if your little tab doesn't work right, do what I'm doing. Just delete it. I'm going to say add icosphere again. And before I click on anything else, why is this not letting me control? I think I saw Randy have a question about that, or someone had a question about that earlier, that they couldn't control the parameters of the icosphere. And why is that happening to me? I went through all this last night and everything worked perfect. That's really annoying. Is anyone else having that same trouble that I am? Yeah. What is going on? I don't suppose any of you have a hint.
I was focused on something else. What is the issue?
Oh. Yeah, so what could be the problem? Yeah, well, okay, so let's not worry about it. I'll work around it.
I'm just wondering what doesn't work.
I know the solution.
So when I click on add icosphere, there's this control panel that pops up over here, and it's supposed to let me edit the values there.
Okay.
And it's not working. And Adam, I'll tell you, it's not this version of Blender or Cell Blender because it worked last night. I was able to make this work last night.
Wrong day. Okay. It doesn't work on Tuesday, it's 13th. On Linux as well, it gets lost. Yeah, but scaling works with mouse.
Yeah, scaling will work. Okay, so we're going to work around it. This is annoying and it's going to slow us down a little bit, but it's we can work around it. Okay, so what we're going to do is we're going to go after pulling this up. We don't need this add icosphere control panel over here. Really, I'm just going to have to let go of my frustration and go to the item control panel, numerics panel, which is on the left, on the right side, way up here at the top. Click on item, and what we can do is we can change the scale factor of the sphere. And right now the scale factor is 1, or we can change the dimensions. But let's change the scale factor to 0.25 by 0.25 by 0.25. I think that's, no, that's not the right scale. I'm sorry. I'm going to hit, okay. We're going to type in 0.3125. 0.3125 and 0.3125. Okay, and that's going to give us a sphere that's 0.625 microns in diameter. So this is the diameter or the size of the bounding box that would contain the sphere. So there it is. And we did that by going to this item and setting its, we could either set its dimensions directly or we could set the scale. And you can see that it's not quite totally symmetric in X, Y, and Z because it's not really a sphere. It's really a sphere made of polygons, right? Okay, so now let's go back to the Cell Blender tab and let's change in the model objects panel, let's left click on it and choose the icosphere. And we know that the icosphere is chosen because we can look up here in the upper left-hand corner and see that it says icosphere. That's the name of the currently selected object. And here in the model objects control panel, we can see it says active object, icosphere. Let's click there and change its name to CYT, capital CYT for site. That's the name that it was given yesterday in the organelle transport model example that Jim showed at the end of the day. We called it site. So let's call it site. And then after we've named it site, then go to the list below there, which is the model objects list. And let's click on the plus key. And the plus key says model object include, and it says include objects selected in 3D view window in model objects export list. So if we click on there, the name site appears in our list. And in the list, we have some options way over on the right-hand side. And one of the options looks like a little fan folded color swatch thing. And so let's click on that little fan fold, and that assigns a material to it, and the material is white. And then I can click on the white tab, and it pulls up the color of it. And the color can be RGB or SHV or hexadecimal number, but under say HSV, doesn't matter. Under HSV, it's HSV A. A is the alpha value, which is the transparency of it. And right now you can see it's opaque, so we can't really see inside it. So click on that and set the alpha value, which is the opacity, set that to 0.2. And when we do that, now we can see through the surface of our object called site, and we can see the release sites of A and B inside. And if I single step through time, we can see, or if I single step through time, we can see there's our molecules of A, B, and C inside, viewed through the transparent object called site. Okay. And someone said, does the subdivision setting affect the area of the triangles? Yes, it does. And what I would have wanted to do was subdivide this one more time so that it had more triangles, but it'll work just fine for what we're going to do here with this number of triangles. So it's not a big deal. But I am a bit annoyed that seems to be broken, and I'm not sure why it's broken. We'll figure it out later. Okay, so now we have site, our object called site as a model object. Okay, no more questions. Is anyone having trouble that I should interrupt that we should interrupt for a moment to take care of? Hopefully everyone is getting this so far. Okay, so moving forward, if I hit play here, you can see the molecules are diffusing right through it. Well, that's because we haven't rerun the simulation with this object called site included in the simulation, right? We just created it now. We added it as a model object, but we haven't saved and rerun the model. So I'm going to save the model. I'm going to go into run simulation and clear the previous runs and hit export and run. That takes a moment, and there it goes, and now it ran. And if I hit reload, if you know, you can see I have time stopped, you know, at this moment in time over here, and there's particles outside. But if I hit reload, now the particles are inside, because this is that same moment in time where we left it, but with the new simulation result where the site object is included in the simulation. So let's rewind time and hit play. And now you can see we have containment of A, B, and C within our object. And with that, not too much time, the A and B molecules become kind of well mixed, and they start reacting in more of a well mixed condition. And then, of course, the C molecules, you know, start forming near their initial sites of creation, but then over time, now they're being kind of created everywhere as A and B react in more of a well-mixed condition. So what's that result look like? We can go into the plot output and generate a new plot. And so now here's our new plot. And look, we're getting almost completely there after just 1 millisecond of simulated time. Remember, we're running for 1,000 iterations with a microsecond time step, so this is only 1 millisecond of simulated time. And you can see the shape of this is kind of more exponential in shape, but still, I bet it's not perfectly an exponential. Well, it has a low hook at the beginning, and I bet it's too fast at the beginning relative to the end, but it's kind of hard to eyeball it now because it's becoming well mixed so quickly. Okay, so let's get ready for our next step. When we release molecules of A and B, we release them from a non-well mixed, you know, point source condition. What if we wanted to release them starting as initial conditions, starting as well mixed within the object called site? We can do that. If we go to our molecule placement and go to molecule A, for our release, we can say at site colon A, or that's one of the acceptable ways of expressing it. Or I can say A at site. So Jim, if you're there, do you have an opinion about what is the more proper way to seed the, or add the species to the model in BioNetGen language? Would you normally say A at site, or would you say site at site colon A?
If there, I mean, I think it's fine what you're doing now, as long as these are unstructured molecules, so it's the same function.
Right.
But
yeah.
I mean,
but in general,
does it allow that?
Yes.
I would use that then.
Yeah, these are both allowed. Yeah. So the syntax has the same meaning and interpretation as it does in BioNetGen language. So this at site means if this were a complex molecule with many molecules bonded together, this at site applies to the entire complex. It would put the entire complex in the volume, in the volumetric compartment called site. Okay, and Adam, if I do that here, does it matter whether I choose spherical or not?
It doesn't really matter.
Okay.
In fact, when you specify the sphere as the cytosol, the compartment is set automatically.
Right. Okay.
Okay, so in this case, you don't need to specify the compartment for the A because it automatically knows, okay, I appeared in this volume, and this
Right.
volume is called site. So,
Yeah.
so it sets the compartment automatically.
Okay. So let's use that syntax. When you use that syntax, then a lot of the rest of this gets ignored by the exporter when we export the model, and we'll change the layout in here so that it's more context sensitive and less confusing. But for now, just keep in mind that if you use the BioNetGen language compartment syntax here for expressing the molecule, then the rest of this is ignored and doesn't matter, except for of course except for the quantity, of course.
Maybe I can clarify. Okay, so in this, it's a kind of new feature. So in this case, the main specification here is that it's spherical and the release location is 0, 0, 0. So the molecules will be released at the position 0, 0, 0. And the compartment will be set automatically.
Okay.
It will be ignored with a warning.
Okay, yeah, thanks for that. Yeah, okay, so this isn't ignored then. Yeah, I think this is not ignored, but the compartment for A is automatically set from BioNetGen's point of view. But I think what we want to do is we want to say object region and then say site here. And so now there's some redundancy. I say site here and I say at site there. And if I do this, there's some redundancy and I could possibly lie, right? I could say release in site, but put a different compartment here or put a different compartment there and lie. And we don't currently detect, I think, whether you are lying or not. And
yeah, in fact, actually the compartment specified by the molecule is ignored. It is set to wherever the molecule appears.
Okay.
Yeah, so maybe we should clarify this and make some.
Yeah. Okay. But I think there's a reason why I want to keep this here for now. Yeah. So this is the first year we're teaching MCell 4, and things are a little bit different. And so I'm sure I'm confusing many of you with our own kind of confusion about this, but there are some deeper complexities to this that I won't. I think I better not confuse you even more with. So let's just leave it like this, and I think in the testing I did last night, this is going to work the way I want it to work and the way I want you to learn it. Okay, so we're going to name the compartment here, and we're also going to release inside a shape. So the important part here is that instead of saying a spherical release, right, we're going to release inside a shape given by an object or a region. And this is a named object, and so you have to give a name. You have to give the name of a named object in your model objects list here. Okay, site. And when you name it like this, what this means is to take the molecules of A and uniformly distribute them throughout the shape of that volume, regardless of what shape it is. It could be a really crazy snaky shaped thing. Your molecules of A will be beautifully uniformly distributed throughout the entire thing. And you'll get 1,200 of them, just like we asked for. So this is going to take molecule A and distribute them uniformly within site. Okay. And we're going to do the same thing with B. We're going to say, at site colon B, and we're going to say object region, and we're going to name the region called site, CYT, in all caps. And we're going to get 1,000 of those. Okay. And that's all we need to do. And now we can rerun the simulation. I'm going to hit save. And I'm going to say export and run. And here we go. And there it is, running, it's finished. And now when I hit reload, watch what happens. So this is, I'm at time 0 right now. Here's where they were initial conditions last time. And when I hit reload, now they start at time 0, uniformly distributed throughout the volume. And now when I run it, the C molecules are created by these reactions within a well-mixed compartment like that. And when I go to the plot output, here's what we got last time. I'm going to hit plot, and here's the new plot. Let's get rid of that one. So here's what we had last time, and here's the new one. And you can see there is a subtle difference in the shape. Here it started slower and then built up. And this one actually started faster. And I think this is starting slower because it's taking some time for them to start to come together. And even though the ones that are coming together are more concentrated at first over here, there's fewer of them, right? And so the rate of reaction, the overall rate of reaction is actually slower here than it is here. Here they're starting well mixed, which is a lower initial concentration than with them all together, but they're all well mixed and they're all accessible to each other. So we get an overall greater initial rate of reaction. So that's an interesting result. Okay. So we're going to save that. Okay. Here we go. So the next step in our model is to, now we're going to create our first organelle to be inside the sphere, inside the site. So let's go back to model objects. And we're going to create a new icosphere. And again, I don't know why I can't do that. Okay, that's really pretty awful. Maybe there's, I don't know. I'm gonna zoom out, and I'm gonna go into item. And for this one, we're gonna change its size. Let's change its dimensions to be, I think, 0.3 by 0.3 by 0.3. And I think that's the right size for this guy. I'm just going to cheat for a second. So one of the items that you have in your in the materials that we sent out to you is a cheat sheet for this model, which is a diagram that shows this is what we're going to build today. I could have started with this to help you see what we're going to build. So, but here we call the compartments cell, organelle 1 and organelle 2, but to make things quicker and tighter and easier to write in BNGL, we're calling it site and O1V and O2V. And then, of course, we have the membrane compartments, which we'll talk about. So the radius of the cell, 0.625, so its diameter should be 1. Okay, that's a mistake I made, I think. Let's change that right now. So I I think I want the scale. So let's select, before we work on the organelle, let's select the object called site. I see a mistake I made. Let's set its scale factor to 0.625 by 0.625 by 0.625 for the 3 scale factors. So it's about a 1.25 micron diameter object. And then let's select the other object, which is still called icosphere. And let's set its scale to be 0.6. And 0.6. Oh, wait, that's, I think that's wrong. 0.3. I'm sorry, I keep confusing myself. The scale 0.3 by 0.3 by 0.3. I apologize for being a little bit clumsy here. And then let's set its location. It's here, its Y location to be minus 0.25. So that matches what we have on our cheat sheet here. Its radius should be 0.3. So that means its scale should be 0.3 because the default scale radius is 1. And the Y value for its location should be minus 0.25. Okay, so this is now what our model looks like this. And now let's go back to Cell Blender and change the name in the Model Objects tab. Notice that it says the active object is icosphere. It's the selected object. And if I click on its name here, I can change its name to capital O1, capital V. So O1V, organelle 1 volume. Okay. And then after we've done that, then go to the Add Model Objects button and hit plus to add it. And so now we have O1V as a model object. We can click on its color swatch once and then twice to change its alpha value to be 0.2 again. So here's our organelle over here. And now we need to rerun the model. So if I run the model here and hit export and run, there it goes. And if I go to the plot output, well, if I hit reload, there we go. And if I go back to time 0 and hit run, we have molecules of A, B, and C interacting, but we have this object in here acting as a boundary, kind of blocking off part of the space. But when we release the molecules of A and B, in the molecule placement, A and B, we released A and B both inside site. And so because they're uniformly distributed in site, using this syntax, the way it works in the new version of MCell 4, the molecules of A and B are actually inside the cytosol, but not inside the interior of the organelle. But it's kind of hard to tell that that's true. I believe that's true, but it's kind of hard to tell because of the transparency of everything. But I think it's true. Okay. So now let's change the model and change it so that the molecule of B, instead of being released in at site, if we say at O1V, and then object regions, type in O1V there so that these two things agree with each other. And I'm going to save the model. And now I'm going to run it again, clearing the completed runs and hit run again. Now, with molecules of A released in the cytoplasm and molecules of B being released inside O1V, when I look at the plot output, what we're going to see is nothing happens because we've now spatially segregated the two compartments from each other. We have molecules of B inside here, and if I hit reload, we can see there's the molecules of B inside O1V, and the molecules of A are only located in the cytosol, and they're not located inside O1V. If there were any A's inside there, we would have reactions, and we would see A and B, being consumed and molecules of C being created. But that's not what we see. We see that there's the membrane of O1V acts as a reflective barrier, an impenetrable barrier to diffusion. B are contained inside here, and the A molecules are contained inside the cytosol, and A and B cannot access each other. So they can't collide, and there can be no reaction. Okay, so now we have an interesting situation that occurs in cells where we've got some molecules contained in one compartment and other molecules in another compartment, and we would like to let these two molecules, react with each other in some controlled way. So what we're going to do now is we're going to, well, I'm going to, this is the next milestone in, this is the, I guess, we had milestone 0. We skipped over milestone 1. We already passed it. This is milestone 2 in our construction process. So if anyone is lost or stuck, at this point, you could grab the milestone for milestone 2, and I think it would be right at this point. I'm pretty sure it would be exactly this situation. Okay. So let's continue. So what we're going to do now is in the molecules, we're going to make another kind of molecule, and we're going to call it T1 because it's a transporter, and it's going to be a surface molecule. So let's change it from volume molecule to surface molecule. We can see its icon changes to a little grid text, like a surface texture icon. And let's give it a diffusion constant of 1e minus 8. So molecules, protein molecules in membranes have diffusion constants that are quite a bit slower than in free solution. Typically, 10 to the minus 8 or 10 to the minus 9 centimeters squared per second has been measured using single particle tracking technology to watch the motions of proteins. Okay. So now we have our transporter T1 defined. Let's write a reaction for T1. So T1 is going to be a reaction, and what we're going to do is we're going to say A at out, plus T1. It goes irreversibly, irreversible reaction goes to A at in plus T1. And this is a new proposed syntax for that's more general and more generalizable, and we're proposing this as an extension to the BioNetGen language And I think, we've discussed it at great length, and Jim and Sinan helped design this with Adam and I. And at some point, this will be added to as an official part of the BioNetGen language. And what this lets you do is, instead of having to always say what the name of the compartment is, where this the specific compartment is where this reaction is allowed to occur, here you're just saying it, A on the outside of any membrane that contains T1 will transport A across the membrane to the inside of any compartment that contains T1. That way, if I have a model that has, say, 1,000 compartments in it that all have T1, with the existing syntax, you'd have to name all those compartments and write down 1,000 different reactions, right? And if you did it this way, you'd only have to write the reaction once. And then wherever you put T1 on any surface, that surface becomes a place where transport can happen from outside to inside. Okay, and then the rate constant that we're going to give this is 1E8 for that reaction. Okay. And if I write that, then the only other thing I have to do, actually there's two things I have to do to make this work. I have to go to the model objects and choose O1V, and I'm pretty sure to make this work, Adam, correct me if I'm wrong, is I have to now start to specify the relationships between the compartments like you do in BioNetGen language, but in a slightly different way. Here, we're doing it from the point of view of the volumes, and the volumes have a parent. So for site, site has no object parent because it's the outermost one, but O1V has as a parent the object called site. And here, rather than having the plasma membrane be the parent of the volume that contains it, here we have O1V. Its parent is site, and O1V has a membrane name called O1M. So we did this in a slightly different way here, and in a certain sense, this information from Cell Blender's point of view, since we have real geometry and that we're creating, this information shouldn't be required of the user to type in. This information should be deduced by because this is real 3D geometry that has real topological relationships between them that are set by the scene that we've just created. And this information here should be invisible to you and not touchable by you, and it should be deduced by the topology from the topology that you made. And that way, the topology speaks for itself. In BioNetGen language, of course, all you have is the language to describe what you have. And of course, you have to tell it what you want to create. But here in Cell Blender, we've made things in 3D from real structures, and those structures speak for themselves, and we shouldn't have to say anything more about it. And if we did, we could possibly lie and be inconsistent with what we've created, right? So in a future version, we'll probably make this information be invisible because you shouldn't need to see it. Okay, but
just for MCell, this is not required. This is required only for export to BNGL.
Yeah.
At least for the reactions that we have there right now. Okay.
So Adam, you're saying I don't have to put these here? Maybe let's see what happens if I leave these out. But what I do need to do though what I am going to do though is choose. What I'm going to do is, if you're following along with me. So Susanna says site is a 3D encompassing volume, and O1M is the 2D membrane, right? And we're about to make that explicit here. I'm going to first choose the object called site in my list over here. And I'm going to make it invisible by clicking on this little invisibility button. So that makes it invisible. And then I'm going to choose O1V in our model objects list, and then move my cursor back over here. And then what I'm going to do is on the keyboard, I'm going to hit the tab key on the keyboard. And this takes me into what's called edit mode. And the tab key takes me in and out of edit mode. And in edit mode, you can see we have little, the edges highlighted and little highlights on where the vertices are for this object. And now in edit mode, if I hit the A key on the keyboard, oh, no, I'm sorry. If I click outside of it, it unselects. If I click outside of it with the left mouse button, it unselects everything. And if I hit the A key again, it selects everything. So click outside, unselect, hit the A key, it selects everything. So make sure everything is selected. And then over here, when we notice that when we went into edit mode, oh, well, you can't see it, but you'll see it in a moment. So below the model objects list, there's a list below that says define surface regions for O1V. So whatever the currently selected object is, which is O1V in this case, we're going to see what surface regions it has. And and to make a new surface region, and you can see the list is empty, to make a new surface region, I'm going to hit the plus key to add a new surface region. And the surface region is going to be called O1M. Okay, so now I'm being explicit about saying that the entire surface of O1V is a region called O1M. So we have to be richer in our definition of surface regions when we are explicitly in 3D as we are in MCell, because we have the capability of creating surface regions that are a subset of the whole surface of the object. In this case, we've designated the entire surface of the object to be the region called O1M. Well, we've just named it, and what makes it explicit is I now click on assign. I have to click on, and what it says is assign selected faces to surface region. So if I click that, then it happens, right? And the way we can find out and prove that it happened is we can click outside the object to unselect that, and then I can go over here and I can click on the select button here in the define surface regions control panel, and it says select faces of selected surface region. So the selected surface region, if this was a list of more than one, I could pick the one I want, and I can say select the faces that are a member of O1M. So I hit select, and there they are. So that shows, and if I hit deselect, it didn't. This is because I'm not in face select mode, but don't worry about that for right now. Let's see, how do I get to face select mode? Where's that? Ah, okay. So if you follow my mouse, this is getting to be a little bit deep here, but I'm trying to show you how to make surface regions on objects, which is an important aspect of creating 3D models. If we go up here to the upper left-hand side, we see that we're in edit mode, and this is where we can switch between object mode and edit mode. And the tab key is a hotkey for that. And then next to that are three little buttons. The first one says vertex select. Next one says edge select. And the last one says face select. If I click on face select, we are now in what's called face select mode. And if I say, select the faces and then deselect the faces, you can see that we're now selecting and unselecting all the faces that are a member of O1M. Okay, so that's that. So now we've created a surface region called O1M and assigned all the surface to it. And from the point of view of wanting to make a model that's compatible with BioNetGen, this is what we have to do. So it's easy to make a model here that would be not compatible with BioNetGen, right? I mean, not with BioNetGen, but with non-spatial, solvers, right? It would be very easy to do that, but let's construct the model in a way where it's consistent with the concepts from in spatial and non-spatial models. Okay. There we go. All right, so now we have a region called O1M. And so now when we do the molecule placement of, let's go to the molecule placement tab. Okay, so to recap, we've created a new molecule, a surface molecule called T1. And we've added a surface region to O1V, and that region is called O1M. And we've made that O1M be the entire surface of the object. Then in our molecule placement, I can add a new release site with the plus key, and we're going to release molecule, and we're going to say at O1M colon T1. And the reason why we made the region called O1M is because we want to be compatible with the BioNetGen language model that we're going to run later in BioNetGen. And there, the compartment for the surface is called O1M. So we want to make sure we're consistent with that. And then when we release T1, we're going to release it on the object region. And we're going to say O1V, and then we're going to say square bracket O1M. So this square bracket syntax is how we refer to the surface of this surface region of O1V. So we have a slightly different way of expressing this concept here in MCell. And our way of doing it here predates when we started working with Jim's group and learning about compartmental BioNetGen language. If we had known at the time about it, we probably would have chosen a syntax here that was compatible with what they had, or at least worked with them on coming to consensus on how to do this in a different way. But and then how many do we want to release? We're going to say we're going to release 700. Okay, so we've created a third release site that's going to release at O1M colon T1 on the object region called O1V square bracket O1M. Now, what's more powerful about the way we can do things here, or more general, I shouldn't say more powerful, but more general about the way we can do things here is O1M, or whatever region this is, does not have to be the entire surface of this object. As you saw in the model of synapses earlier today, we can put the AMPA receptors and NMDA receptors within the synaptic contact area. And it was a region of the surface. It was a sub-region of the surface. And we can, later today, before we close, we're gonna turn O1M into a sub-region rather than being the entire thing. And you're gonna see what happens with that. Okay, so someone's asking how to change the size and radius of O1M, of O1V. And the way you do that is select O1V. You can tell that it's selected because its name is up here, and go to the item control panel. along the side here, and then you can change its scale. The preferred size here is 0.3 by 0.3 by 0.3 in scale factor, and its Y location is minus 0.25. Okay, that changes it. Okay. Okay, so here we are, and now we are ready to run the simulation. We have set the amount of T1 that we're releasing to constant number 700. I'm going to save the model. Oh, and before we get out of here, I'm going to go back to the model objects, and I'm going to make site be visible again. So just click on the little eyeball icon next to it to make it visible again. Like that. And then I'm going to go in here and say run simulation. Well, actually, no, not just yet. Oh, yeah, we're ready because we added the reaction. Also, A at out plus T1 goes to A at in plus T1. So now we're ready to run simulation. Uses unknown compartment O1M. Yeah, so I think, Adam,
Okay.
I think it is necessary. So I think this is what I found last night. So back in the model objects panel, for the object called O1V, we're going to make its parent object be site. And if I hover over this field, you can see it says parent object. And if I hover over the field next to it, it says membrane name, which is the membrane name of the surface object. And so its membrane is O1M.
Just to clarify, it was needed because it was used in the molecule placement.
Right. Yeah,
Oh,
exactly.
okay.
Yeah, I guess that's probably the reason why. Yeah. Okay. So there may be simpler ways of teaching this part of the tutorial, but I think this is okay. Okay, so now we're ready to go in here. I'll say clear completed runs and run it again. So the molecule is not called T, it's called T1, Michael. And okay, there it is running. And just to remind you and others, T1 was added as a defined molecule, and then it was added as a reaction where we said A at out plus T1 goes to A at in plus T1 with rate 1E8. And then in molecule placement, we placed at O1M the T1 molecules in the object region O1V, O1M. Okay. So we ran it. I'm going to hit reload. Okay, this is what it looks like. So there's our surface molecules of T1 in the surface of the cell. And if I run this and look closely at this, okay, we can start to see molecules of C accumulating inside O1V. There they are. And previously, we saw that we didn't get any molecules of C being created because of the segregation. We added a transporter. And now in our plot output, when I run it, now we see we're getting some molecules of C being created and some consumption of A and B. Of course, now it's slower, right? And the rate is limited by the limiting step, right? What's the limiting step? The limiting step here apparently is the rate at which the transporter can transport A from the cytoplasm inside to the interior or the organelle. Okay. Okay. So now let's add.
Maybe Tom, sorry.
Yeah, go ahead.
Just break now for 2:30.
Yeah. Okay, perfect. Yeah, thanks for interrupting me, Adam, and reminding me. So yeah, let's take our 2:30 break, which what looks like, where is it? It looks like it's supposed to be a half-hour break. And when we come back, we'll be on a new Zoom channel, and we'll work fast and hard to finish our model here.
Thank you very much, Tom, for announcing the new Zoom channel. Yeah, we will be back at 3. Yeah, am I right?
Okay. Yeah, 3 o'clock.
Yeah, my brain is just going slow.
Yeah, so 25 minutes from that.
And Tom,
Okay.
may I ask, can you make a like milestone 2.5 from this?
So yeah, I'll make a milestone. Well, this will be, yeah, this is milestone 2.5, and there'll be a milestone 3 that's already listed there, but I'll make this milestone 2.5. Okay, so I'll do that right now.
So there's a little more in the milestone 3. So
Yeah. So let me do a save copy as milestone 2.5 up 2.5. Save it, and then somewhere back here I have an SCP command. There it is. 2.5. Okay, it's there. Very good. Okay, and I'll stop sharing, and I can stick around for a few minutes if anyone has questions. If not, I'll take off and see you at 3 o'clock.